Thanks a lot. So thanks a bunch, first of all, to the organizers for making it possible to speak here. Special thanks to you and Jean for making it possible for me to be in Korea. So far, so good. I haven't been able to see much, but it's been great so far. So, okay, so I'm going to talk about a generalization of the classical Theorem problem that I'm really fond of, these so-called Berge hypergraphs. I'll define them as well in a moment. You have to bear with me. Apparently, I created these slides in landscape mode. I'm not sure how I managed to do that, so sometimes we may see some funny slides, but I think we'll manage. Okay, so I'm going to start off with a couple basic notions, basic definitions here that I hope are generally familiar, but I'll just remind us anyway what they mean. So fix a graph F. We call a bigger graph, generally a bigger graph G, F-free if it doesn't contain F as a subgraph, just so I don't have to keep saying doesn't contain as a subgraph, F-free. And we intentionally choose F. I like to use the letter F for this graph here because it'll be the graph that's forbidden, right? F-free. So the typical question here in Turán problems or extremal graph theory is, what's the maximum number of something, in this case edges, that you can have in an n-vertex F-free graph, right? And sort of the typical starting question everybody's seen before is, how many edges can you have in a graph on n vertices with no triangle? And it's pretty easy to come up with a construction that has a lot of edges, right? Take your complete bipartite graph here with classes of the same size, n over 2. You get n squared over 4 edges. And you can prove that this is the maximum as well. There's an upper bound that gives you this as well. Okay. And so here's two of the many theorems of this type. Generally, the starting point here is Turán's theorem. This is sort of a slightly weak version of it that's stated here. That if you're absent, if you have no clique on k vertices, the maximum number of edges you can have here is n squared over 2 times this multiplicative constant that depends on k there, right? That matches what we saw here in this little example here, right? When k equals 2, when k equals 3, you have a triangle, that coefficient becomes a 1/2, and you have n squared over 4. Okay. Then there's this far-reaching generalization, the Airstone-Shimonovich theorem, or sometimes Airstone, or sometimes Airstone-Shimonovich, or sometimes I like the fundamental theorem of extremal graph theory, because it's really fundamental. It says a lot, right? If you take a graph F, and it has chromatic number k, then the upper bound on the number of edges is approximately the same as if you only forbid a complete graph on k vertices. So the chromatic number is what's sort of important here, not so much the structure aside from that. There is, of course, the error term, that little of n squared. So if you have something other than a clique on k vertices that's k chromatic, there might be additional edges you can add on. But as n tends to infinity, it basically is the same upper bound as the kk graph. One thing to note here, and this will be important later, is when k is bipartite. Notice actually what happens in both cases when k equals 2. In Turán's theorem, when k equals 2, I mean, this is a ridiculous statement. It's asking for the maximum number of edges in a graph that doesn't contain an edge. So the upper bound is 0, as that actually spits out. Shimonovich, it does give some information. The leading n squared term there disappears, right? 1 minus 1 is 0. So you're left with little o of n squared in the bipartite situation. But a lot of effort has been put into proving theorems about extremal numbers for bipartite graphs there. They have different orders of magnitude. We generally know things better than little o of n, and we'll see a couple of those throughout the talk. I want to identify that scenario, though. That's kind of what we call the degenerate case, right? Because this theorem is sort of degenerate. It doesn't give us much information. So when the chromatic number of the forbidden graph lowish, we're in sort of a degenerate scenario. Okay, so I want to generalize these types of theorems and this type of thinking to hypergraphs. And I want to go into too many details in the general theory beyond the specifics here. But in general, hypergraph extremal problems are very, very difficult. Sort of problem number 1, what's the extremal number of the 3 uniform smallest complete graphs, say on 4 vertices? Even that we don't know. So I want to go in this different direction here of this so-called Berge hypergraphs. I'll define these with some pictures. It's reading that definition out there. It's not that hard, but it can be misleading. So this is an attempt to make problems tractable, actually solve some things here. Okay, so what is a Berge hypergraph? Well, fix a graph F. In a moment, this is going to be our forbidden structure as well. And we call another hypergraph H a Berge-F if you can come up with this nice bijection between the edges of F and the edges of the hypergraph H in such a fashion. So I like to think of my graph and my hypergraph as being on the same vertex set. And I'm asking, can the edges be mapped to hyperedges? So each edge of the graph is associated with an edge of the hypergraph in such a way that that graph edge is inside of the hyperedge. Okay? So let me add sort of two alternative ways of thinking about this, and I'll draw a little picture here. Even if it's clear, it's worth seeing a few pictures just to get comfortable with this notion here. So one other way is if you start with a graph and you just grow all the graph edges by throwing some vertices into them, you'll end up with a hypergraph, right? All the edges will be larger, and that'll be in Berge-F. The bijection's clear, just map the hyperedge to the edge that I built it from. Or the other way that I actually prefer to think about it is in reverse. If you have a hypergraph, it's a Berge-F. If to each hyperedge you can choose two vertices, turn that into a graph edge, and then produce your graph F. Okay, so let me give a couple examples here real quick. So let's say F is just a triangle. Okay. And let me give a couple examples of hypergraphs that are Berge triangles. Okay, this is something I want to emphasize here. A Berge triangle is not a unique hypergraph. Many graphs achieve being a Berge triangle. So one simple example is sort of a natural. I don't really want to think about the uniformity of these hypergraphs, so I'll just draw my hyperedges as large, but it could be any fixed R. So here's a simple one. Right. You have three hyperedges. Let me use another color here. And I suppose everyone can see the bijection here to the triangle. I can map that pair to that red edge. That'll be mapped to this hyperedge here. Those two will be, this edge will be mapped to this hyperedge, and this edge will be mapped to this hyperedge. So I found the triangle among those. Right, there are other vertices here that were maybe candidates for something. Okay, so that's one example. Let me show some others here. How about something like, so this is a pretty natural triangle. Right, let me show something that's a little less natural. Say we have something like this. Say we have one hyperedge that contains those two, another hyperedge that contains those two, and a third hyperedge that contains all three. Right, so there's some ugly overlap here, right? This sometimes wouldn't be considered a triangle in the hypergraph sense in some occasions. In Berge, it does, though. We're still okay, because the natural embeddings are these two, and then these two are adjacent to each other inside this one that happens to contain all three. So if my hyperedges contain extra stuff, it doesn't cause me any problems. Okay? And maybe just one more simple example, just furthering that idea there. And this is sometimes useful. So maybe I have three vertices, and maybe they're all contained together, right? They're in the intersection of all three hyperedges. This clearly counts as a triangle as well. I have a few options for my bijection here. I can associate any way I like, but I can very simply get my triangle. Okay? So something I want to emphasize here is that a Berge-F is a bunch of things simultaneously, right? It's a Berge triangle is all of these and all of the other pictures you can come up with. In fact, if you don't specify your graph as being R uniform, there's basically infinitely many pictures you can draw here that are a Berge triangle. Okay? I guess if it's R uniform, there's only so many graphs, hypergraphs you could create, and so there'd be some amount. You could actually count them. That could be interesting, I guess. So the idea here, this can be done for any graph. I hope it's clear that it wasn't specific to my triangle here. And this notion was introduced in order to generalize existing definitions for Berge cycle and Berge path. Berge cycle and Berge path were defined in a slightly different way, which you had an ordering of vertices and an ordering of edges, and there were some intersections required. This definition here captures that and sort of takes the notion and generalizes to any graph here. Okay? So we can ask the similar question to before we forbid a graph F. Now I'm going to forbid a hypergraph F in a sense here. So hypergraph H is Berge-F free if none of its subhypergraphs are isomorphic to any of the Berge-Fs. Okay, so if I was looking at a 10 uniform hypergraph that contained no Berge triangle, it wouldn't contain any of these pictures and any of the other ones, right? So it's forbidding a bunch of stuff simultaneously. That's important to keep in mind. Another thing that's worth noting is a hypergraph, like maybe these aren't great examples, but if you have a hypergraph, it can be a Berge-F and a Berge-T and a Berge-G. It can be a Berge many different structures, right? Just imagine I had like 10 hyperedges all containing the same 6 points. I could create all sorts of graphs on that set there. Okay, so there's overlap between these classes as well. Okay, so this is the notion. This is the notion here. We're going to forbid this structure. So generally, we're going to be forbidding a bunch of hypergraphs simultaneously from a graph. Okay. Now, what does this allow us to do? This allows us to prove some concrete theorems here. So the first here, R is going to be the uniformity throughout the talk. Oh, this notation I didn't define, did I? Didn't define it. I hope it's clear, but let me jot down what I mean by this here. So Berge, I think you can probably guess, though, from the notation from before. So this quantity measures what is the maximum number of R uniform edges on n vertices you can have with no Berge-F. All right? Okay, so max number R edges on n vertices without Berge-F. So without any Berge-F, right? Those many, many, many different copies simultaneously. So we'd like to determine how many you can actually have. And we have this first sort of, let's call it a version of Turán's theorem here, that if the uniformity is smaller than the number of vertices in that hypergraph, sorry, the number of vertices in the graph, not in the hypergraph, in the fixed graph KK, then the quantity is approximately this thing here. I'll give a hint why it's that. I suspect you may see already why it might be that. This result, it's not due to Erdős and not due to Gerbner-Palmer. It follows from separate results from those two papers, and it just falls out easily from those. So this is not really a difficult result here. Donny may speak. Donny Gerbner is a sort of talk related to this, counting subgraphs, which is a related problem here, and may actually, I don't know if he's going to give proof of that or something, but it's connected. I see him sort of winking there, so I guess we won't know till tomorrow. But. So here's another version here that's a kind of Airstone version for Berge hypergraphs. Okay, so now we've got F is a graph that's k-chromatic, and that k again is larger than R, and then the extremal number is basically the same here. Okay, this tilde means asymptotic too. Okay, k minus 1 choose R, n over k minus 1 be R. So again, forbidding a Berge-F that's k-chromatic, the base graph F is k-chromatic. I don't know what the chromatic number of the Berge thing is. I'm not even going to speak of chromatic number of hypergraphs. So the extremal number is approximately equal to the quantity when you just forbid the Berge KK. Okay, so let me give a hint at least why the lower bound here makes sense. It's not difficult, but again, it's worth seeing a picture here. So maybe it's actually worth asking the audience. This this quantity here, does anybody see what's by that quantity by any chance? So you have k minus 1 things, and you're choosing R of them. Right? I want to create R edges, a hypergraph with R edges. Or what's your favorite graph in extremal graph theory? We can just take that. Yeah, we're going to take basically a Turán graph, right? So although it's going to be a hypergraph here. So this is going to be the construction. Let's take k minus 1 classes of size approximately n over k minus 1. And I'm going to make an R uniform hypergraph on this by just taking one vertex from R classes at a time and creating a hyperedge that way. Okay? So a hyperedge might look something like this. Whoops. I don't know. That's one vertex, one vertex, one vertex, one vertex. Right? If you think about it for a little bit, the number of R edges in this picture is exactly k minus 1 classes, choose R of them, and then from each of those R classes, choose one of the n over k minus 1 vertices. Okay? So that is my construction, and it's not hard to see, but it's worth going through. Is this Berge, let's say KK free for now? Yeah, did you have a question?
What is the subscript R?
Excuse me?
What is the subscript R?
Oh, here? That means that I'm restricting myself to R uniform hypergraphs. Right, so the base graph I'm looking at is R uniform, and and it only makes sense to the forbidden Berge ones are all R uniform as well, simply because hypergraphs that are not R uniform wouldn't occur in an R uniform hypergraph anyway, so I don't have to worry about whether they're. So strictly setting to the R uniform setting. And actually, it's a good question because let's look for a second of R equals 2. R equals 2 is the graph case. And if you think a little bit about that Berge definition, a Berge-F, when R equals 2, is just F itself. What's the embedding? You just map edges to themselves. And these both spit out the appropriate bound. When R equals 2, look at what you get. You have n squared. The k minus 1 choose 2. The k minus 1s cancel. You get n squared over 2 with n, and you have k minus 2 over k minus 1. Right? That should be the right amount. Well, you can check it. So. But it should give the same statement as in Turán's theorem. Okay? Yeah, so I want to convince you that this is Berge k free. Okay? And again, it's pretty easy to see, but it's worth thinking about how we establish that things actually are free. This argument will essentially work for F being any chromatic number k as well. Okay? So suppose for a second that it actually contained a Berge kk. Right? There's some subhypergraph of this that was a Berge kk. That meant that if I look at that subhypergraph, maybe I'll put it in blue here. and look at the bijection that establishes that it is a Berge KK, it means that I can embed each of the edges of the Berge KK to the edges of a KK. Right? So that means that somewhere in this graph lives a complete graph on k plus 1 vertices. But if there was a complete graph on k plus 1 vertices, at least two of its vertices would appear in one class together, because there's only k minus 1 classes. And then it would mean, well, one of the hyperedges of this Berge KK got mapped to that pair. But was there any hyperedge that contains both those vertices? No, not by construction. The construction of my hyperedges used one vertex from each class. So there's no hyperedge that contains both of these. So this edge never existed in my graph there. And the same thing works if I had F instead of KK, because the K color classes of my F would appear here, and two color classes would be sort of stuck in, or at least two vertices of two different color classes would be in here. Okay. All right, so that at least gives basically the lower bound to both of these. The upper bound, again, it follows from other results not related to Berge by Mubai and Verstrada and Olochikaman, who were looking at related but different questions, but happen to imply something in this sort of, again, non-degenerate case when k is larger than r here. Okay? When r is greater than or equal to k, we call this the degenerate scenario, much like the degenerate case in graphs. We have similar situations where we no longer have this nice bound. And actually, in hindsight, this bound would have been nicer to write as less than or equal to this plus little o n to the r. That would have been a superior way to write this, because then when r is greater, this choose function here is 0, right? It vanishes, and I'm only left with the little o to the r, n to the r. And that's all we know in general in the reverse there, is that it's not n to the r order of magnitude, it's something smaller, but how small and what behavior, that we don't know exactly. So I want to talk a little bit about those. Okay? All right, so I'm actually going to go back in time now. Those other results were kind of more recent. So I mentioned before the Berge, this general definition was introduced to generalize the notion for cycles and for paths and so on. And so here's basically the first result on Berge cycles. So if you read a Berge C2K even cycle, the maximum number of r edges that you can have is approximately n to the 1 plus 1 over k. And the constant term's not known here. It's been improved a bunch of times here, closer and closer and closer to what might be the truth. One issue here is that in general, even the ordinary extremal number, we don't know what the upper bound is. I mean, we know an upper bound of that order of magnitude, but we don't know the truth. That's not really what I want to get at here. What I really want to get at is that the ordinary extremal number for the C2K is 1 plus 1 over k as well. So it looks very much like the graph case. So these sorts of things can happen in the degenerate situation. Keep in mind, right, in an R-uniform hypergraph, you in principle have access to n to the r many hyperedges. You have access to way more hyperedges. So dropping down not just below n to the r, but all the way down to sub-quadratic is a major drop here in this degenerate setting. And the next here is a major motivating factor for why these questions are interesting in the degenerate situation. Because the other result of Dury and Lemons is the following, that if you forbid an even cycle, you also get the same order of magnitude as an upper bound here, n to the 1 plus 1 over k. That's surprising, right? In the graph case, that is not the order of magnitude. Anybody remember? Forbid an odd cycle, how many edges can you have, roughly? Anyone? N squared, right? Just take this picture. This one right here works, right? So that is the upper bound there. So there's a discrepancy here. So these Berge hypergraphs don't act exactly like graphs, even in the degenerate situation. Okay, all right. Here's another sort of Erdős-Galai type result. Forbid a path of length k. So the subscript k there means number of hyperedges as opposed to number of vertices. In this case, I know there's an ongoing debate. Never mind. So this basically gives the complete answer to the maximum number of r edges you can have. And here it doesn't matter whether r is greater than or equal to k. We basically have a full understanding. Actually, these are both sharp as well. If n satisfies the appropriate divisibility conditions, basically if those quantities give you an integer, there's a corresponding construction with the same number of hyperedges. In fact, if you look at what's written here, n over k, k choose r, and so on, it's highly suggestive of what that construction is. So if you're bored now already, try and figure out the constructions there. They're not hard, but they're of some interest there. Okay. So like I said, this is basically Erdős-Galai for Berge paths. Okay. And just to compare here, Erdős-Galai says that the max number of edges in a pk-free graph are 2 times n, and that basically matches, I think, the first bound there. If we allow the the restriction on R to go further down and plug in what it should be, I think it spits out k minus 1 over 2n. It should. It should. Okay. Okay. Okay, and so here's another direction that's not quite formed in the typical a typical extremal fashion here. Now I'm forbidding path cycles of length k and longer. So I'm allowed cycles of short length, but nothing of longer here. And a series of papers here by Kostochka, by Fure de Kostochka and Luo, and Kostochka and Luo, give upper bounds on the maximum number of hyperedges you can have in this case. You can write this in the extremal format, exn Berge this, but we're restricting cycles of longer lengths. It's a little awkward to write it in this fashion, okay? To my knowledge, these are not sharp, so this is still an active area of research here. It's just another way of looking at these problems, okay? So we talked about paths. We talked about cycles. Another good category of graphs is complete bipartite graphs. Certainly when we're thinking about the bipartite scenario, that's sort of the next example to go and look at. And I have two propositions here that talk about that, and I want to flesh this out a little bit more in a moment. So first, we know that if my uniformity is large, bigger than s plus t, remember this is still the degenerate situation, right? Because the degenerate situation for a bipartite graph is as long as r is greater than or equal to 2, the chromatic number of the graph that I'm forbidding. So r in this first proposition, greater than s plus t, certainly that's going to be bigger than 2. Maybe I should have said s and t are both at least 2 as well. Then the extremal number here for the Berge KST is n to the 2 minus 1 over s, which matches the bound in the graph case given by Cory T. I call this a proposition here. This follows from a more general theorem that maybe, I think I'll even prove. It's very, very simple, but I'll explain how it works. Again, talking sort of in this fashion here, why we have that upper bound, sort of in much more general setting. And then another result here for uniformities that are small, so at most s and at most t, we get this different order of magnitude, still n to the n, little o of n to the r, right, as we know from what I stated on the earlier slide. And we have some idea that it's n to the r minus something there. We don't believe that's the truth, though. We think that the exponent's even smaller than that. But this is better than just simply saying n to the little o n to the r here. And you'll notice these two still don't fill out the whole theory here. What if r is between s and t? Then there's actually nothing other than little o of n to the r as well. So there's still sort of work to be done. Before jumping ahead, then, let me state and basically prove a more general proposition that resembles the top proposition up there. Again, it's simple, but it's a good way of seeing how these function. Maybe I'll leave those. So the statement is the following. I'll call this a theorem, although you'll see from the proof that maybe it's not deserving of that name. So fix a graph F, and fix a graph F and integer R that's at least the size of the vertex set of F. Okay, R is going to be the uniformity of my hypergraph here. Then the Berge extremal number, R uniform, n Berge F. So if my hyperedges are big enough, then the quantity of this guy here is at most the ordinary extremal number. Okay, for graphs. Okay, just to emphasize here, that clearly implies this proposition here. That's really what's being proved in that one. R is at least s plus t. S plus t is the number of vertices in a ks plus t. And the order of I could have written a better bound than big O of n to the 2 minus 1 over s. I could have said at most the extremal number of it. But you just plug in Cory T to that guy there. Is it okay? I saw you furrowing your brow there, like I think this should imply that guy there immediately. And let me give a rough idea how you can prove this. It's really quite simple, and it's a typical strategy for these problems. So what I want to do is, let's say we have H is a hypergraph, is Berge F free. Okay? And I'd like to say that the number of hyperedges in this H does not exceed this guy here. So I'm going to do a very simple strategy. I'm going to try and convert this H into a graph that has the same number of edges and then say, oh, that graph is F free. And therefore, this has that bound. And just saying those words almost is the proof. So how do I do this? I'm going to make heavy use of that fact there. Okay, so the strategy is the following. Embed, and I'll convince you that I can do this, but embed an edge. So when I say edge, I mean a graph edge. So embed an edge into each, let's even say this, embed a unique edge into each hyperedge of H. Okay, so let me just draw a little picture here. Over here, right? So I've got some hyperedges of my hypergraph. I don't know, something like this. And I want to attempt to embed a hyperedge into each of them, thus creating a graph. And I want to embed a unique one. So if I'm already embedded edges, say I'm doing it greedily. So say I reach this hyperedge here, say this has already been embedded for this hyperedge. I don't want to reuse that one. So I don't want to keep them non-overlapping. So I mean, this picture, it's easy to do, but let's say I take that one, and then this goes to this hyperedge, and then this one takes this, and so on and so forth. Okay, so I want to be able to embed one for one. Why might I not be able to do that? I might not be able to do that if I reach a point where here's my hyperedge H. Here's my hyperedge, and every single pair already has a red edge embedded to it from the previous steps of the greedy algorithm. All right. So say everything's been used. All right. Okay, I can't put everything. So nothing's available. All those came from previous hyperedges in the embedding. But then this thing here is a KR, right? At least in the graph sense. I have a KR embedded to that thing there. But each of these edges corresponded to a hyperedge that contained them. So that means my hypergraph contained a Berge KR, okay? Which it's not hard to see. If you contain a Berge KR, then you contain a Berge KF, because F is on this many vertices. But let me take a step back and make it even easier than that. If I contain a KR on these things here, I definitely just contain an F. Forget about Berge-F, just think about F. R vertices, R is at least the number of vertices in F. A complete graph on the number of vertices greater than this contains F. So among some of these edges, there's an F. Those individual edges that correspond to F correspond exactly to a Berge-F. So that's a contradiction, right? That means that I should be able to always find an empty pair that I can embed to. I can keep embedding, keep embedding, keep embedding. So once I've done that, this creates a graph G, and that G, that is, well, this is the end of the proof, but that is F-free. And the number of edges in G is exactly the number of edges in H, right? I embedded one for one, okay? So, well, so square, right? I said it. That finishes the proof there, okay? There's various improvements you can make to this idea here to push this guy down here. You notice we embedded one edge for one. If you can embed more stuff, sometimes you can make improvements. And if I have time, I'll try to do that in a later proof here, or at least sketch it, because that's where it actually gets really interesting. Okay. All right, so that's the sort of more general theorem that's actually hanging around there. All right. Yeah, so just to reemphasize here, if my uniformity was not this big here, I could attempt this strategy, but there'd be no guarantee that it would work, because maybe I tried to embed and there were nothing available to embed to. Well, so what? Then I got a K, R. Let's say R was much smaller than the number of vertices of F. There's no guarantee that I get this F that was forbidden in that case. Okay. So I want to talk a little bit about the non-uniform case. And historically, somehow this was the original direction that this problem was approached in, where we looked at hypergraphs that weren't R uniform, yet hyperedges of any size permissible, even sizes depending on n. Maybe you had hyperedges of size log n, or root n, or even linear in n for some reason. And then you said no Berge-F, which now contains really an enormous class of graphs, right? If you allow hyperedges of all different sizes, there's a lot of different things that can be Berge triangles. Forbid all of those, how many hyperedges can you have? So the first issue was, how do you measure the size of hypergraphs that are non-uniform? I mean, one, you can just count the hyperedges, right? That's no problem. But it's actually more interesting if you count the following function instead, where you have a weight function on your hyperedges, and you compute the sum of the weights. The simplest weight is just the size of the hyperedges, right? Add up all the sizes of the hyperedges and try to make that as big as possible. Then there's some sense in introducing hyperedges of size log n. They contribute a lot. Although one issue is when you have large hyperedges, they seem to make it easier to find forbidden graphs. Because remember what the Berge thing is, you have lots of pairs of candidates for embedding. And so big hyperedges can be problematic. Okay? So this is a different version here. By the way, I'll make a few mentions of it as we go on, but changing the weight function here So changing this to instead of size of h, but some function depending on the size of h or something else, is very interesting and very little is known there. I'll mention a few results though, to sort of pique your interest there. Okay, so here's an early theorem. Well, early, I mean, it's from a year, 2 years ago. I mean, so early in my mind maybe is I think of it here. And it's very much in the vein of this guy here, okay? So it says if you're not necessarily uniform, but all your hyperedges are of size at least r, right? Then the sum of this function here is at most n squared, as long as your hyperedges are large enough. Now here, unfortunately, it seems like at first you can just repeatedly apply this theorem to get this to work, but that doesn't work, right? You can't apply this to each uniformity of here and larger because there's too many uniformities, right? I mean, there's not a constant many values that the uniformity can take on. R can range all the way up to n, right? So you need to have a little bit different strategy in order to make that. This does imply, I believe it should imply this one, more or less, not quite. So they're closely related to one another, okay? And this does imply a type of uniformity result of this type. It says if you are uniform and R is just big, then just pull out any one of the uniformities. No single one can exceed n squared, right? Because all of them summed up together, with the hyperedge sizes included, don't exceed n squared. And I mentioned this form because actually it's pretty cool here. So as long as the hyperedges are large enough, bigger than the vertex set of the forbidden graph, you get n squared. But you can do even more here. So this result here by Gross, Matuku, and Tompkins says something really cool here. Look at the differences between these two statements here. So f is still just a fixed graph. Oh, yeah, there's a typo here. That e as an edge of e of f is redundant. That's not used in the statement of these. So you can just cross this bit out. That doesn't come into the way that I've stated here. So your hypergraph is Berge-F free. In the second statement, though, your hyperedges, the uniformity is large. So what's R of f? This is the graph Ramsey number for f, right? This is the minimum n such that any two edge coloring of kn will contain a rainbow, not rainbow, a monochromatic. That would be very hard unless you had a small graph, right? A monochromatic copy of f, right? So generally, right, R of f is going to be much larger than V of f, but it's exponential, say, right? Then the number of hyperedges is little o of n squared. Not n squared, up to n squared, little o of n squared. So the order of magnitude drops down sort of suddenly there when you cross that odd threshold there. Technically, they proved something a little bit better. They proved the Ramsey number of f versus f minus an edge. That's what this minus edge business was there. But, I mean, who cares, right? So, no, that's sort of mean. But it's for simplicity's sake, I stated in this fashion here. And this actually begs an interesting question here. What if we keep pushing up the uniformities? Say you're log n uniform or something like that, really big. I think, personally, that when you get up that high, you're going to have bounds like n squared over log n instead of little n squared. And we actually have some results of that type I'm not going to go into now. Okay. All right, so this is a specific theorem that generalizes this notion here. I want to flesh it out here and try and give, when was I supposed to wrap it up by? 310. Okay, great. Then I'll try to give a sketch of a slightly weaker bound that's given here because it generalizes this idea and it's again pretty cool here. Okay. All right. So first, let me explain why it's being stated in this fashion here. So here you notice the weight function is a little bit different. It's the size of the hyperedges minus 3 instead of just the size of the hyperedges. I want you to observe two things. First of all, it's closely related simply to the size of the hyperedges, right? If you split the 3 off from that sum, you get sum of the size of the hyperedges minus 3 times the number of hyperedges, of which we already know something about. So it's related to that one. But the real reason it's put in this format is to answer a slightly different question here. Now I'm going to allow multi-hypergraphs, so I allow edges to repeat, and I make no restriction on edge sizes here. If I do those two things simultaneously, if I don't subtract a 3, this question becomes really silly really fast. Because look at what hypergraph I can construct that doesn't have a C4, that has lots of hyperedges. Take 3 vertices and take infinitely many copies of the same 3 vertices. All right? If I don't subtract 3, I get the upper bound of infinity. This doesn't contain a C4, obviously. There's only 3 vertices. Right? So that's one of the reasons to do this minus 3. There's a historical reason for it, too. There's a count of another problem in graphs that's an h minus 2 for a similar trick. Let's not worry about it too much. It just makes the computation easier for what I'd like to give here. Okay, so I want to do a similar strategy to this one. It's just the upper bound, and I'll prove a slightly weaker upper bound. I think the upper bound that I will give here will be maybe root 3 n to the 3 halves. The constant doesn't really matter for the argument here, okay? So I'm just going to call this, let's go back up the right, the proof here. So I want to use the same notion as before where I embedded an edge to each hyperedge. But if I embed one edge to each hyperedge, at the end I'll have created a graph with as many hyperedges, with as many edges as hyperedges. That doesn't solve my problem here. I want to know the sum of the hyperedge sizes, right? Not the total quantity of hyperedges. Remember, some hyperedges might depend on n. So rather what I'm going to try to do is embed many edges into each hyperedge. Okay, so I'm going to say, let's say try, and then I'll convince you I can do it. Try to embed a large matching into each hyperedge of H. Okay, so take H to be a Berge C4 free hypergraph, and to each hyperedge, I want to try and embed a large matching with the same conditions as before. So if I embed this matching to this hyperedge, a different hyperedge should have a different matching so that they're totally edge disjoint from each other. They may share vertices, so like luckily in this case I could take those two there and I'm still safe, right? Okay, so let's say large pairwise edge disjoint matchings into each hyperedge of H. And I'm going to do this greedily as well. And what's large mean? Large here is going to mean of the following size. The size of the hyperedge minus 3 divided by 2. Okay? Divided by 2, certainly divided by 2, right? Every matched edge takes up 2 vertices at once. And I'm going to have 3 vertices potentially left over at the end that get nothing matched among them. Okay? So I'd like to prove that I can do this at every step. So can we even do this? Well, let's look why we might not be able to, or how we're going to achieve this. So here's, say this is my pending hyperedge, HI. Say I've already embedded a matching of this size into hyperedges H1, H2, H3, H4, all the way to HI minus 1. Then I reach HI. I make this little claim that among 4 vertices of this HI, there's a free edge. Okay? So among 4 vertices in HI, there exists an unused edge. Okay, unused in the sense that it didn't appear in a matching of any of the previously embedded ones here. If I can prove this claim, then this will give me this quantity here. Because what does it mean? Grab 4 vertices, there's an edge that's not used. Embed to it. Now ignore those 2 vertices, which have been accounted for. Look at 4 more vertices, right? Even including the 2 that I looked at before, just not these 2. And those 4 have an unused edge. Embed another, grab another 4. And then at the very end, you might be down to 3 vertices, and I make no further claim here. So that's my H minus 3 over 2. This you can take ceiling if you want here, but okay. So let's prove that claim. Okay. So suppose not. Suppose we reach 4 vertices, and this is very simple to check. Suppose you reach 4 vertices, and there's no free edge. Right? So these are the 4 vertices. It means I have a K4 on these. Every single edge has been here, and we have 2 cases. I'll justify the first case and hand wave the second case. So case 1 is that all 6 of the hyperedges that were embedded here came from only 3 hyperedges in the previous steps. So what I'd like to think about is each step, when I embed a matching here, color that matching with a color corresponding to, say, the index there. So the first hyperedge, all of the edges matched embedded to it get color red. The second one's blue, third one's yellow, fourth one's green, and so on and so forth. So here I'm trying to embed a matching of this size in color I. So case 1 is that used 3 colors. Okay? You can't cover all the edges here with 2 matchings. It takes 3 matchings to cover them. So since we have colored chunk, let's actually look what it looks like. So if you have 3 colors, there's no choice but to look like this. There's only one 3-edge coloring. White, say. So here's my K4. But that means that the hypergraph that corresponded to blue edges contained all 4 vertices. The hypergraph that corresponded to red edges contained all 4 vertices. The hypergraph that contained white contained all 4 vertices. And the hyperedge HI that I'm working on also contains all 4 vertices. So I've got 4 vertices contained in 4 hyperedges. I'm definitely going to be able to create, don't forget, a Berge C4. Right? I can make any. This corresponds to this example here. Right? So this can't happen. Okay? This case 1 is impossible. Case 2 is that, okay, so maybe they weren't all together here. Maybe I used them up by having 4 or more colors, right? 4 or more hyperedges were involved. So used at least 4 colors. I'm not going to prove that one, but it's easy to show that if the hyperedges here are all colored with 4 different colors, you can find a path of length 3 with all 3 different colors. Okay, so then there exists, now I get to say rainbow. A rainbow P3. Okay, so what's a rainbow P3 look like? Looks like that. This is color 1, color 2, say color 4, I don't know, 3 different colors. These 3 appear in a path inside of these 4 here. Can someone tell me where my C4 is in this situation? I've got a hyperedge that contains this one and these 2 vertices, a hyperedge that contains these 2 and these 2 vertices, a hyperedge that contains these 2 vertices. Where's the 4th hyperedge? What's that? HI, yeah, HI has everything. So HI could be that one there. So there's my C4, I'm not allowed. Right, so this, I mean, yeah, so you have to convince yourself there's a rainbow P3. It's not hard to do that, it's a tiny bit of case analysis. So that proves my claim. Among any 4 vertices, I can find a hyperedge and I can keep greedily embedding them. So I can get this. All right, now we're almost done with the proof here. Yeah, perfect. Almost done with the proof. This creates a graph. Actually, creates a really cool graph. All right, so now I've created a graph that has a number of hyperedges. So E of G has exactly this for each hyperedge of H. It has that many edges. G is properly edge colored. This is really cool, right? Remember I said each time I embed this matching, I give it a unique color associated with that hyperedge, HI, blue, and so on. But it's a matching, right? What do edge color classes look like in a proper edge coloring? They're a matching, right? None of them touch each other. So this is actually properly edge colored. It's colored with a lot of colors, right? It's colored with 1 color for each hyperedge, but nonetheless it's properly edge colored. I make a claim, which I won't quite prove, but I claim that G is not C4 free, but K24 free. Okay? So I claim that it's K24 free. Let me show you why. This actually involves a very cool bit of anti-Ramsey type problems that are interesting in their own right. But let's say it had a K24, or more generally, say it had a K2T. T was something we could figure out. Right? So it has this. So a bunch of vertices down here, and all edges, right? Okay, I don't want to draw them all, but it's properly edge colored. So the edges on colors of these edges are 1, 2, 3, 4, up to T, say, without loss of generality. The colors on these, there may be significant overlap, but we know that the edge color of that is not 1, right? It's something other than that one. They may use the same T colors shifted in some fashion. But if you think about it for a little while and look at this, C4s live in abundance in this picture, right? Here's a C4. Right? You have all these nice zigzagging C4s. And what happens is if you have a properly edge-colored K24, you're going to find a rainbow C4 inside of it, just greedily if the number is large enough here. In this case, 4 is large enough, but you can find it here. You just can't color it and avoid it. Okay? So it's K24 free, as otherwise G contains a rainbow C4. Okay? So that's the interesting anti-Ramsey question in general is, what if you properly edge color something? How big does that something have to be in order to give you rainbow copies of something, right? It's like the reverse. That's why I kept saying rainbow before, right? So, okay, so why is that a problem? What happens if G contains a rainbow C4? Anybody tell me? So G is that graph I created. I have a rainbow C4. Right? We've already kind of seen it, but that means I found a C4 in it. I'll use numbers now. 1, 2, 3, 4. But what's this guy? You can probably guess even if you don't see it. This is a Berge C4. Each of these, that edge came from hypergraph 1, from hypergraph 2, hypergraph 3, hypergraph 4. So it can't have a rainbow C4, so it can't have a K24. And now here's the dirty trick of the whole proof here, is what's the extremal number of K24? Fortunately, it's basically the same as the extremal number of K22, right? That's where I get the square root 3, right? The result of Furedi says the extremal number of n K2t, well, let's say just K24, is at most, it's 1/2 root 3 n to the 3/2, this plus this big O n, right? But that's an upper bound on that. And just all you have to do is multiply both sides by 2. And you get this sum here is at most, the 2's cancel, root 3. So not root 2, root 3, okay? So how do you get that to root 2 instead of root 3? You try a different trick. Instead of embedding single edges, you try to embed triangles. A bunch of triangles is slightly denser than a bunch of edges. But then all this coloring business breaks down because that's not a proper coloring anymore. You have to do some other tricks there. Okay, but that's how you improve that bound there, okay? There's one or two other slides, but I'm just going to jump to the end here and leave maybe those problems on the board here. These sort of implicitly were implied by what I stated throughout the talk there. But the first is Berge C4 in general, still not known. A sort of big meta question is, when do the two extremal numbers differ from each other, right? We saw odd cycles, they had this gap, but even cycles, they were the same. Give us a better characterization of when this happens. And then this last problem was that business about as the uniformity gets to the size of the edge graph, gets up to the Ramsey number, even goes further, what starts to happen with this thing? Does it drop below little o of n squared? How far down does it go? Okay. I'll leave that there, but thanks everyone for your attention.